Hey, I'm back. I'm sorry for the delay. A little bit of technical problem here. I think I got it. All right. Well, welcome back, guys. All right. I'm sure you read, hopefully, the email I sent you concerning the rest of the week that we have, the rest of the weeks, I should say. We're down to the wire. We're at the almost at the end. We're in chapter 14, which I'll complete today, and it's fairly short. We probably won't, we're definitely not going to use the whole thing. But we will now start initiating what are called study days. So for those days, and let me double check here, let me call up. Yeah, for these days, starting today, obviously I'll finish chapter 14. And then Thursday, we're not gonna be done with it, but if we need to, we can continue with chapter 14, but if not, it's gonna be what we call a study day. A study day is basically this. I will be here for you, so you can come in with questions or we can work over problems and so forth. This is your time, and we can have a number of these study days. This generally happens when we have lectures during exam days. Normally, if we were face-to-face, those exam days, obviously we're taking the exams on campus, but with online, it really has the advantage that it allows us now to have a number of days at the end of the semester that we can utilize for you. Okay, so we'll have one this Thursday, that's the 18th. And then when next week, next Tuesday, also be designated a study day. That works out. Now, these aren't mandatory, as I stated. This is for you. That works out pretty good because it's the beginning of the break, Thanksgiving break, and a lot of people take that time, to get ready for family and everything. So I'll be here, but if nobody's, shows up, we say within half hour or so, I'm gonna go ahead and shut it down. Unless you're late and you want to send me an email, and then, I'll make special time for you to come in if you need some help with some questions. Obviously, the 25th, we have Thanksgiving break. We won't be here. I won't be here, okay? And then when you come back on that Tuesday, the 30th, we will do chapter 15. Short chapter, we'll probably more likely finish it that day. And then that Thursday, which is the December 2nd, is designated another study day. And then the following week, the 7th, designated a study day, or if we have to, finish up chapter 15 if there was some leftover from the previous week. And then the 9th, another study day. And then finally, the 14th, that is the final. So you need to, that is the last day to complete all assignments. If you've not done any assignments, and there's a number of you that have not, they are still available, as I stated before. There is a late penalty involved with them, but they're still available. So, some points is better than no points. So you can go back and knock them out. Okay. And so the 14th is our final exam. I need to get everything finished, and I believe they gave me 2 days so I can get the grade. So that is the absolute last day for any completion. Now, plan ahead. If there's a problem with the 14th with respect to work or something like that, the only time I can do the exam earlier if needed, but I cannot do it later than the 14th. Okay, so plan ahead, look at your work schedule if you are working and you need to reschedule the exam for you. Like I stated, I can do it ahead of time, but I can't do it after the 14th. All right, any questions about that? Okay, you all have a copy of this, there's no surprises. Take advantage of this time. This is a good time to prepare for the final, get ready for it. There is on the course website a review for the final exam. There's 60 questions. It is all multiple choice. All right, the question types are very similar to the ones we have done. with the exception that there's no, writing in your own words, all multiple choice, okay? So, any questions about that? This will get you in preparation for that. All right, no questions? Well, let us continue with where we left off, and I left off with Coulomb's law. Now, the takeaway from this is we're not going to get involved into detail, into a lot of detail about this equation. It's basically, if you think about this, this is basically a measure of force or attraction between two items, two molecules, two magnets. A good example would be magnets. If you take two magnets, of which I do have here, well, that we did. Yeah. Okay. I take two magnets and, I put them where they're, north or south and south, and I can feel that force as they repel. Well, as I bring them together, slowly, I can start to pick up that force of repulsion. And as I drive it even tighter, you can feel that force really get strong. The same is true the opposite. If I were to put a north and south together, and as I brought them together, I would feel nothing as they're far apart, but the closer they come together, I can feel that force of attraction really build up. Now, that force of attraction is governed by this relationship. That is that the force between them is proportional to the charge between these two entities, in this case, the magnets, okay? And they could be the charge between two ions or two magnets. And so the greater the magnitude of the charge, as the magnitude of the charge increases, the force of attraction increases proportionally. And that's what they mean by proportions, directly proportional. As I increase one magnitude, one variable, the other variable increases, okay? Now, it's also what we call inversely proportional to the distance squared. But what that means is that when a variable is inversely proportional, it's basically telling you this. As one variable goes up, the other variable goes down. And more specifically, it goes down to the square of the distance between those two forces, which is really can be very dramatic with respect to the force. And it's governed by this equation here. Now, not to be concerned about Q1 and Q2. They're just simply the charge, okay, of two entities, whatever they may be. And K subscript E is simply just a constant. Now, what I can do to simplify this equation, I can just say that the force, I can combine the Q and the K, and I'm going to make one big Q and just one big constant, but keep the R there, R squared, all right? So that Q, big Q, is not going to change. Okay, it's just going to stay constant. Now, if I start with R equals 1 unit of distance, and it doesn't make a difference what the units are. It could be 1 centimeter, 1 micrometer, 1 nanometer. It's 1, okay? So what that means, if I plug 1 into R, and that is the radius, it is Q, I meant to put Q on the side, divided by 1 square. Well, you know that 1 square is 1 times 1, which is, guess what? 1. And so the force by having a distance of 1 unit is simply equal to Q, which is a combination of the two charges in K, just a variable, okay? Now let's do this. Let's increase the distance by a factor of 2. Let's double that unit distance. So it goes from 1 to 2. It's double, right? Well, now what happens? The force is equal to Q again, divided by 2 squared, which is simply Q divided by 4, right? 2 times 2 is 4, which is another way to look at this is simply that the force reduced by a factor of 1/4 of whatever Q was originally. It really dropped it quite drastically by a quarter, 0.2%, really dropped it by a quarter of whatever Q was to begin with when it was a unit of 1. Okay, so as we increase the distance between the charges, that force interaction gets drastically drops. Now let's go the opposite direction. Where we started, where R was 1, let's cut that in half. So now R is equal to 0.5. And so now this is the first example, second example, third example, where force now is equal to Q divided by 0.5 squared. And that, if you do the math, ladies and gentlemen, is a factor of 4, meaning that the force, by reducing that distance, that radius by half of what it was originally, you have increased that factor, that force, by a factor of 4, quite large, okay? And you can see that when you play with the magnets, that as I bring those two magnets together, whether it's attraction or repulsion, as I bring them closer and closer together, if they're being repelled, that you can feel that force repel. Okay, pretty strong force, strong enough to run a lot of electrical trains that run on magnets to lift them up, to lift big, heavy stuff. Okay, so that's a takeaway from this force, that basically from this equation, it's Coulomb's interaction, in that the interaction between two species, in this case, two charges, is proportional to the magnitude of the charges and inversely proportional to the square of the distance, the radius between the two. Okay. All right, so now we've been talking about IMF interactions. These are intermolecular forces. Okay, and these are forces that molecules have with each other. Okay, now we could be talking about intermolecular forces, and that is forces with molecules with each other, or intra meaning what is the force that holds a molecule together. So to answer these questions, we have to first discern, are we talking about the bond, or are we talking about how these molecules interact with each other? So you got to read the question carefully. All right, and so if they're talking about how the bond is made, then it's straightforward. We can say it's either ionic bond, or a polar covalent bond, or a non-polar covalent bond. That's it. Okay. If we're talking about the interactions with other molecules, then we have to discern, okay, if it's non-polar, because if it's non-polar, we're going to assign to it the London dispersion forces. Okay. If it's polar, has a polar bond, and it is not hydrogen bonded to nitrogen, oxygen, or fluoride, then it is a dipole-dipole force. Okay. And if it is hydrogen bonded to nitrogen, oxygen, or fluoride, then we're talking about hydrogen bridging forces. And then fourthly, if we're talking about an ion in an aqueous solution, and more 99% is an aqueous solution, then we're talking about the ion dipole force. Okay, so we have to discern that. So the first one says, what holds the atoms together in one ammonia molecule? And so they're talking about here one molecule. What is holding the atoms together in one ammonia molecule? It's not saying anything about ammonia interacting with other molecules of ammonia. So it's being asked, what type of bond? Okay. And we know it's a nitrogen-hydrogen bond, which automatically, two different atoms, automatically it's a polar bond. Okay. Polar covalent bond. Here it says, what is holding sodium ions in water? Here we go, sodium ion and water being the dipole. So we got ion dipole forces that are holding the sodium ions in water. What is holding three HCl molecules together? Okay, keyword 3. So obviously we're talking about the interaction of molecules, HCl molecules with each other. So we have to define or assign to it one of those 4 forces. Obviously, the ion dipole cannot be given because there's no ions in here. It's simply hydrogen chloride or hydrochloric acid, HCl. All right. We know that HCl has a polar bond, 2 different atoms. So we can eliminate the London dispersion forces. So we eliminated ion dipole, we eliminated London dispersion forces. The only 2 choices left are either dipole-dipole or hydrogen bridging. And as I mentioned, for hydrogen bridging to be selected here, it has to be hydrogen, which we have here, H, but it has to be hydrogen bonded to either nitrogen, oxygen, or fluoride, of which HCl does not fit that category. Therefore, it only choice left over is a dipole-dipole force. You see how we went about that process of elimination and figure out which one it is not by eliminating the forces that it cannot be, okay? What is holding the ions together in salt? Okay, so we're talking about just sodium chloride. There's no mention of water, so we're talking about solid sodium chloride. So the only thing is we got a metal, non-metal. The only choice we got here is an ionic bond. That's it. Okay, ionic bond because it is a metal and a non-metal. What is holding 4 H2O molecules together? So here we go. 4 H2O molecules, we're talking about intermolecular forces. Okay, so we got that. Nothing there about sodium or ions, so dipole. So we got that the ion dipole is not a choice. So now we know, hopefully by now, that H2O is extremely polar because it has polar covalent bonds. Okay, so that eliminates again London dispersion forces, eliminated, ion dipole eliminated. So as we did for the previous one, it's either dipole-dipole, hydrogen bridging. Well, hydrogen bridging, we got hydrogen, we got oxygen, it's hydrogen bridging, okay? That's the forces holding the 4 water molecules together. What holds the nitrogen gas molecules to each other? Keyword to each other, we are talking about intermolecular forces, okay? All right, so now we have to take nitrogen gas, keyword gas, meaning we're talking about diatomic nitrogen, and 2, which is nonpolar. Nonpolar automatically don't have to go any further. It is London dispersion forces. Remember, all nonpolar species, all nonpolar compounds, the only force they have is London forces. And the bigger the nonpolar force is, let me restate that, the bigger the molecule of a nonpolar molecule when comparing a small one versus a bigger one. In the big one, they both have London dispersion forces, but there's more of the London dispersion forces because the other molecule is bigger, okay? And more electrons around. What is holding the oxygens together in an oxygen gas molecule? They're asking about one molecule. Again, oxygen, it is dipole, okay, a diatomic, I should say. Therefore, it is a nonpolar covalent bond. Nothing to do with forces. They're just asking about what is holding the oxygens together in one molecule of oxygen. And then what is holding 2 ammonia molecules together? So again, here we go. We got intermolecular forces, okay? And we got nitrogen bonded to hydrogen. So the only choice is hydrogen bridging force, okay? So much for that. That's how we answer these questions. Identify if they're talking about the bond or they're talking about the force. Once you discern that, identify whether if it's polar covalent or non-polar covalent, or if it's an ionic compound, which then you can assign the force if we're talking about intermolecular interactions or Imf interactions. Okay. This flow chart kind of summarizes it. Okay, we're talking about covalent compounds here. All right. So if it's a polar covalent, non-polar covalent, we just is straightforward. it goes down to this direction. It's London force, London dispersion forces. If the compound is polar covalent, okay, and if they introduce here ions like sodium or some ionic compound, and they're talking about an aqueous system, which is the polar part, then we assign to it ion dipole, okay? If it's not, we got two choices, either dipole-dipole or hydrogen bridging. Hydrogen bridging are only those cases where you have hydrogen bonded to nitrogen, oxygen, and fluoride. That's it. Okay. Nitrogen, oxygen, and fluoride. That means that if it's not one of those scenarios, then it has to be dipole-dipole. All right. So why do we need to know about that? Because that's going to allow us to compare and contrast two different molecules, some physical properties. We're not going to be able to determine the absolute value and say, for example, okay, water boils at 100 degrees because of this force. No, all we can do is say, okay, we got two different molecules here, two different compounds. Which one would have a higher boiling point, for example, or what we call a vapor pressure. We're going to talk about these here in a bit, or surface tension, or what we call viscosity. Okay. Now, the thing to put in your head here with respect to IMF is this: the stronger the IMF, and we're talking about those three: hydrogen bridging, dipole-dipole, and London dispersion forces. Hydrogen bridging is the strongest of those three, followed by dipole-dipole, and then the weakest is London dispersions. Once we determine what type of compound we're dealing with, be it polar covalent, non-polar covalent, then we're able to assign one of those three forces. Then we know, given the strength, that what the effect would be on vapor pressure, boiling point, surface tension, and viscosity. Because think of it this way: if the intermolecular forces are strong, meaning that the molecules are held down to each other tightly, it's going to take a lot of energy to break up that interaction. Okay. Think of it back to my magnets. Okay. If I had some very strong magnets, and there are some superconducting magnets, I used to work with them back when I was in research, strong enough that if you let them come together and they, you know how they close up, they can yank out, and if you got your finger stuck in there, it will yank a chunk of skin off. I lost a lot of skin from super magnets. But these super magnets are hard to pull apart, okay? So think of those molecules as magnets, very strong magnets, okay? And that the interaction is very strong, I can't pull them apart. But if the interaction is weak, they pull apart like these very readily. But the super conducting magnets could be analogous to hydrogen bridging, okay? And London forces could be analogous to these magnets I got, not London forces, but dipole-dipole, meaning that I can pull these apart, no problem. And then London forces could be thought as these refrigerator magnets. They're very weak, extremely weak, and sometimes they don't even hold on to nothing, all right? And as these molecules in the liquid are holding on to each other tightly, what we do by putting energy into the system, we break apart that interaction. And if that's held on tightly, the energy required to pull apart the superconducting super magnets is a lot of energy necessary to break them apart, because that's what we're doing here by putting energy into the system. We're breaking the interaction. You'll see that here in a bit when we show you some graphs. Okay. All right. So vapor pressure. We're all familiar with this. You take a soda bottle. You got about half of it full. I don't have one here with me, but it's capped. You know, you got the liquid in the bottom, and then on top you got airspace. Well, you don't see anything, but there are molecules in there in the vapor phase. If I were to put a pressure gauge on that upper area where the gas is, I would get a measurement, just like you can get a measurement on the air pressure in your tire, because there's molecules in there, okay? And the more molecules in there, the higher the pressure, okay? So this vapor pressure is result of how tightly the molecules in the liquid are being held together. And if they're held on real tightly, then there's going to be less gas molecules in the vapor phase compared to if the molecules are not held on tight, very tight, there's going to be more gas molecules in the vapor phase and the vapor pressure goes up, okay? So when you have strong IMF interactions, you will have lower vapor pressure, okay? Simply because it's straightforward. Think about this, is this. If these spheres here represent molecules that are being held on to each other, they're interacting with each other, and like think of them again with magnets, they're holding on to each other. If they're very loosely held, the energy required is very loose, guess what? We're going to have a lot of more gas molecules. A lot of these guys will be in a gas phase, and the pressure would be higher, okay? So if, for example, we had a pressure gauge, let's say this is my version of a pressure gauge. I got a scale here with a needle, and that's hooked up to that, all right? You know, it's just like a pressure gauge, you put in air in your tire. So if I have a lot of gas molecules in the gas phase, I'm gonna have vapor pressure. Over here, my crude picture, maybe not so many gas molecules in there, so my pressure is like nothing, it's low, okay? Because not too many gas molecules in there, okay? And so by looking at the diagram, you can answer the question saying, which has a weaker IMF? So that would be A, right? Having a weaker IMF means that these molecules in the liquid are held onto each other more loosely, if you will, than B. Therefore, there are more molecules that are being pushed up into the vapor phase, meaning that it would have a higher vapor pressure. A would be compared to B, okay? Compared to B. So with respect to boiling point. Boiling point is that temperature by which that the liquid begins to change from the liquid phase to the vapor phase at whatever atmospheric pressure we're at, okay? And so for water, for example, 1 atmosphere, the boiling point of water would be 100 degrees Celsius, okay? So here to ask you, stronger IMF will have higher vapor pressures. Doesn't that make sense? Think about it. When we go back to this diagram here, if the IMF is very strong, like in B, then as we put heat into the system, energy, we got to break that interaction up. And so that interaction is strong, okay, we're going to require a lot of energy to get these molecules that are in the liquid phase out into the vapor phase. In contrast to A, where that interaction is weak, it doesn't take that much energy to cause these liquid to go into gas phase. Classic example would be compare, I'm sure everyone has opened up a bottle or smelled the bottle of acetone fingernail polish remover compared to, I don't know, something else like water. Water has very low vapor pressure, okay? And if we were to say, get 2 containers with a cap, like soda pop containers, put one with acetone, put one with water, seal it up tight, and just let it sit there for a little bit. If we open the one with the acetone, we will hear the sound, the gas being evaporated, right? We do that with water, not so much. The one acetone is very volatile. Those forces involved with respect to keeping those molecules in liquid phase are much less than water. So the vapor pressure for that and boiling point for, say, acetone, which is part of the fingernail polish remover, is very low compared to water because their interactions are weaker with each other. Okay, and so a strong IMF will give you a higher boiling point, okay, which also gives you a higher melting point for the same reasoning. If it's in the solid phase, the melting point is that temperature in which the compound goes from solid to liquid, okay? And if the interaction is strong, it's going to be a higher melting point. Surface tension. We've seen surface tension here. You may have, where you maybe threw some water, some liquid on the surface of some tabletop, and you may see it bead up, okay? And we call it surface tension. Sometimes the bead is very big. Sometimes the liquid just flattens out. It's not very high. But a stronger IMF will give you, like boiling point and vapor pressure, a higher surface tension, okay? Again, for the same reasoning that the molecules are being held on to each other much tightly than the other. So A represents a higher surface tension, higher IMF. It's pulling the molecules together more tightly than, say, B, where less loosely and the liquid kind of spreads out a little bit better. Okay, a little bit flatter, I should say. Okay, viscosity. Viscosity is the resistance to flow of a liquid to flow. Obviously, oil, as you may not know, is very viscous. And there's some axle greases that look like solids, but they're very viscous. They're oils, but they're very viscous because when we talk about a real thick oil versus a lighter one, the molecules, the interactions for the thick one is very strong compared to the one that's not as thick. So oil flows slowly because it has high viscosity, and something like alcohol and or water, low viscosity. So again, stronger IMF, okay, interactions give you higher viscosity for the same reasoning as the previous two properties, is because the molecules are held on to each other much tighter. Okay. We also know that if, I use the example of water and honey, you get the race, got a cup of water, a cup of honey, and I empty the cups, who's going to win? Obviously the water, right? Because the water is not as viscous. Its viscosity is lower than the honey. But how do we get the honey to flow a little bit faster? What do? We heat it up. And as you heat it up, guess what you're doing? You're breaking up these interactions that the molecules of honey have with each other, and you're making them spread out. So now it becomes more liquidy and more flowing. The viscosity drops. Okay. So you may want to, you may be doing a compare and contrast, okay, of two molecules and answer some questions about it. Like I stated, we can't deal or talk about absolute values with respect to boiling point, viscosity, and so forth, but we can do relative comparison. Well, to do that, we need to know some information about the molecules. One, ammonia, we've done ammonia before, okay, and that was given to you as NH3 as a formula, with nitrogen being the central atom. And when we did using Lewis dot structures, we come up with this particular formula with the lone pair on the central atom, okay? And with that, I said, hey, you know what, guys? Every time you end up with lone pairs in the central atom, you have a polar molecule, okay? Very polar, because even given the fact that you got nitrogen and hydrogen, two different elements, that gives you a polar bond. But some people say, well, this is tetrahedral because of a lone pair. Well, it's not really. What's happening is a lone pair takes up space, so that bond angle here And if this was truly tetrahedral, then the polarity of all the bonds will cancel out and we have a nonpolar species, and that's not the case. Because of the lone pair taking up space, that bond angle is less than 109, and the polar bonds which go toward the nitrogen do not cancel out. So we have a polar species. The other is fluorine. Note it says fluorine and not fluoride. Okay. That tells us that we're dealing with diatomic fluorine. The fact that it is diatomic, two of the same atoms, very quickly tells you I'm dealing with a nonpolar species. Okay. Now, once I know the polarity of the molecule, I can very quickly assign to it the IMF interaction. Nonpolar, automatically London dispersion forces. Okay. No questions asked. That's what it is. Okay. Polar molecule for ammonia. Well, we obviously eliminate LDF because it is polar. Okay. And we have either dipole or hydrogen bridging force. Well, here's the key thing. Yes, there is a dipole there. However, that dipole is between a nitrogen and a hydrogen. And recall, when you have hydrogen bonded to nitrogen, oxygen, or fluoride, you have an additional force which is a lot greater and stronger than dipole, but hydrogen bridging. So we have HBF for ammonia. Now, of the two, HBF is stronger than LDF. So LDF is the weakest of the two. And that hopefully gives you some insight into the four properties that we've been dealing with. Okay. So once we know the polarity of the molecule, we can assign the IMF interaction, which then now we can do compare and contrast of those four properties. But to know the polarity, sometimes you have to draw the Lewis dot structure to determine whether it is polar or nonpolar. Recall carbon dioxide. On the surface, you might think, oh, I got two polar bonds. Okay, this is polar just by looking at it. But that's not the case, because you recall, once we did the Lewis dot structure, yes, it has two polar bonds, but they run in opposite direction of each other, so they cancel out, resulting in a net nonpolar species. And the same was true for tetrahedral, like this carbon tetrafluoride, which has four fluoride bonds, and we might think, all right, four fluoride bonds, definitely a polar molecule, but not knowing the structure which we get from the Lewis dot structures, we can say this is tetrahedral and all four bonds cancel out. Therefore, we get a nonpolar species. Okay. So you got to make sure, if you need to draw the Lewis dot structure if necessary to be able to assign to it whether it's polar or nonpolar. All right, so once we've done that, now we got information. There's the formulas, okay? Here are the forces involved that we just went through. And now we can start answering questions concerning these two molecules. For example, which has the stronger IMF? As I mentioned earlier, hydrogen bridging is stronger. So ammonia has the stronger IMF, okay? If you think about it, having the stronger IMF would mean that they will have higher, three of those four properties, physical properties, would be higher. Okay, so knowing that it has the stronger IMF tells me right away this guy's got the lower vapor pressure, but it's got the higher boiling point, surface tension, etc. All right. Who has the lower boiling point? Well, if ammonia has the higher boiling point because it has a stronger IMF, fluorine definitely has the lower boiling point because it has the weaker IMF, okay? Which one's polar? We talked about that, okay? And ammonia is definitely polar. And then which has the higher vapor pressure, okay? That's the one with the weaker IMF, because more molecules are going into the gas phase. And then if these guys were liquids, which one would be the least viscous, meaning which one will flow a little quicker, and fluorine would be the case. Again, because of the weaker force. And the surface tension, ammonia having the higher force would have the greater surface tension. Oh. Now, keep in mind, the questions asked, which has the stronger IMF? It could have been asked, which has the weaker IMF? Number two could have been, which has the higher boiling point? You know, so the questions could be asked in reverse, okay? All right, so this one probably will maybe summarize all this for you with respect to IMF interactions. As the IMF interaction increases, the viscosity increases, okay? The boiling point increases and the surface tension increases. Again, because as the IMF is stronger, the molecules are held onto each other with greater attraction than when the IMF is weaker, okay? And that being the case, that means that the vapor pressure would be down, would be lower, because less of the liquid will be being kicked up to go into the vapor phase, because too many of them are being held closely by each other in the liquid phase, okay? All right. Does that kind of summarize what we got going there? Brief thing about water, very special water. I did talk a few things about it before, but we did the Lewis dot structure way back when. We found that it has 2 bonding electron pairs and 2 non-bonding lone pairs, if you recall. It had a bent molecular geometry, and that bond angle between the 2 hydrogens is much less than 109.5. Water is very, very polar, okay? And will dissolve most literally all ionic compounds, and some ionic compounds, you know, as we learn about solubility, either 100% or not insoluble. But even the ones that are classified as insoluble, there's always some small material going in solution, because water has that capability. It's very strong in as far as dissolving anything, okay? All right. There's a very strong hydrogen bridging force of water. It is, like I stated, it is a very polar molecule, the most polar molecule that we have, okay? Very high IMF, extremely high IMF, meaning that we have low vapor pressure, which again, due to the IMF, has higher boiling point and melting point, meaning that it will melt, salt ice melts at 0 degrees, and it will continue to until the liquid boils at 100 degrees, has high surface tension. And something interesting about water itself, when it freezes, it actually expands. And the result is the density, remember the density is a ratio of mass over volume. If you were to take a gram of water and freeze it up, and it will float. And it floats because as the ice melts, it expands. Therefore, that volume that was a liquid now is increased overall and has a higher volume. Therefore, that ratio gets smaller than 1, and that ratio of ice is less than 1, about 0.9. And therefore, ice floats because it has a density less than water, which is 1 for water, 1 gram per mil. Here's some crystals of ice. Very interesting structure that it forms. Nature tends to pick the hexagon shape quite often for multiple things. Okay, and then on your right, just a picture of a snowflake, which supposedly are very unique. I don't know that for sure, but that's all I can say right now about that. All right, let's talk about heating curves. And what exactly is a heating curve? what we are doing here is we are making a scale. We're starting with a solid, and then we're going to add heat to it. Okay, we're going to heat it up, and we're going to note the temperature. And so we got data coming here across, and then at intervals we measure with the thermometer. Obviously, we measured the temperature. Okay. Now, if we start with a solid here in the corner of at the 0 point, we have a solid material. And then what happens is, as we add heat to it, the temperature goes up. Makes sense, doesn't it? Okay, temperature's going up as you add heat. Then what happens, something interesting, we reach a plateau area right here. And then as we continue to heat this thing up, the temperature then jumps up and starts to rise again. And until that point that we reach a second plateau. Okay. Note that plateau could be at X amount temperature. It varies from compound to compound. And the second plateau also, if you extrapolate across, would be at X amount temperature also. But there's a plateau there and the plateau there. And then what happens after a time period, after we added enough heat, then temperature goes up again. Okay. So we end up with two plateaus. And this is indicative of a lot of compounds that start with from a solid to a liquid to a gas, as we put energy into it to run it through all the phases of the molecule. All right, so let's talk about this in a little more detail in the next graph. So what is happening here is, as we add the heat, the temperature remains a solid until such time he hits the first plateau, which we could, for example, just treat this as water and say that could be 0 degrees Celsius. Now, on the plateau, we have a mixture of solid being converted to liquid, okay? Prior to that, on the rise, it's all solid until we hit the first plateau. What is happening there is this. We have solid, and this represents the structure of a solid, okay? And as we put energy into the system, we hit a plateau because we are breaking up that interaction. We're breaking up that intermolecular force that's occurring in the solid phase. Now, when all the solid has been converted to liquid, we get the second rise in temperature. So at this point, now we can draw maybe where it's not as ordered. You know, the liquid, if you recall, we had some diagrams before where it kind of distinguished between gas and solid and liquid and gas. And that here represents where the molecules have now separated from each other and is not as ordered as here. Well, as we increase the temperature, we hit a second plateau, okay? And at that point, what is happening, we have a mixture of liquid and gas until such time that all the liquid has been converted to gas, and then the temperature rises again, okay? And this could be, for example, 100 degrees C. That is the boiling point of water, okay? And so at these plateaus, no matter how much energy you put into it, you go from here to here, you're constantly putting more energy here, right? You're going across more heat. You still have a plateau. All of the energy you put into the system is being utilized to break up that interaction between the molecules, to cause it to go from liquid into gas. And just like here, where you go from solid to liquid, the same thing's happening there. All that energy. So a little tip, if you're boiling water, once you got it boiling, just turn it down, because no matter how much more you turn that burner up or that flame, you're not going to get that temperature any higher. When that water boils, it is at 212 degrees Fahrenheit or 100 degrees Celsius. Temperature will not increase until you have converted all that water into gas, and you don't want to do that because you'll burn your pot out. Okay, turn the heat down, save you some money. Okay, so that is the heating curve and what's happening. And to summarize all that is this: is that during the phase change, that's what we mean. Where the phase is changing at these plateaus, going from solid to liquid and from liquid to gas. Okay. At the phase changes, the temperature remains constant. All of the energy is being utilized to break up the IMF interactions of that compound, whatever that may be. It is not, I repeat, it is not, and this is important, we are not breaking bonds, okay? That takes a lot more energy. Remember, these interactions are strong, but not as strong as the chemical bonds that covalent bonds that we have. So we're breaking the interactions, not the bonds. Okay, we're not breaking bonds. So that's an important part to remember that. Okay, please don't write that you're breaking bonds. You're breaking these forces, the IMF interactions. All right, well, ladies and gentlemen, guess what? Congratulations, 14 chapters of chemistry. All right, one more chapter to go and you're good to go. All right, do you have any